Yeah, hi. This video is about analysis of variance for linear regression. So if you were to put your data in Minitab and run it, you're going to get an output called analysis of variance. Looks like this one here. So I want to explain what that is. And first, want to go and you remember probably this and this one, SSYY, which is called the total sum of squares of deviation. It's y minus y bar and square it and add all of these. So that's the deviation from y bar, the square of that, and that's the sum of the square of the deviations. And that's called the total deviations. And probably you remember this one here. That's the y minus y hat. That's the predicted value of y, and that's the actual observation, and the difference squared, so that's the error term, how much, so that's the sum of squares of the error term, so sum of squares of deviations for the error or the unexplained deviations. These are the ones that are due to other factors in the model that weren't included, like in our example we had here. The sales volume versus advertising is like factors like price or economy or competition and so on, where are not explained. And these are the SSR, these are the explained deviations in the model. These are the deviations caused by using advertising as a predictor of sales volume. So here we look at y hat minus y bar, we square it and we add all of these. And it turns out that the total sum of square here is equal to the sum of square, the explained deviations plus the unexplained deviations. So it's equal to SSR plus SSE. So if we put these in the table, and the source here, we have the source of deviation. The total deviation, we computed that 1600.9. We computed the error term, so the difference would be this one here, and these are the corresponding degrees of freedom. For the error term, we used y bar, so we have n minus 1, we had 10, that's 10 minus 1 is 9. And for this one, because we have only one variable to explain our variability, the sales volume, so that's 1 degree of freedom, and the difference 8 is the one for the error term. And these are the corresponding sums of squares of deviations, and here we get the means. So it's this value is this one divided by this, and this value is this one divided by this. And then if I divide, so these are two variances, divide them by each other, I get an F value. This is a new distribution we haven't talked about, but like when we talked about the p-value for the z distribution, we get a p-value for that, and Minitab gives us a p-value which is 0.0001, so that's quite significantly less than 0.05, which indicates a linear model is a good model for this problem. So using advertising and the linear relationship we discovered is a good one for prediction. That's what this says. And what you have here is the formulas that generate this data. So the degrees of freedom, n minus 1, n minus 2, and 1, the regression error totals here. These are SSR, SSE, and TSS, and these ones divided by these values here. So you can see that quickly. So you use ANOVA table to test for a significant linear relationship between sales and advertising expenditure at alpha equal 0.005. That's 0.5%. So basically we're testing there's no linear relationship, which means the slope is 0. And there is linear relationship, which means the slope, the population slope, is not equal to 0. And we look at the test statistic, which is this value here. It's 2625. Actually, we don't need that or this. Let's look at the p-value. P-value is 0.001. That's an alternative way of doing this. So let's since the p-value is less than alpha, then our decision would be to reject H0, and we say at 0.5% significance level there is sufficient statistical evidence to indicate a linear relationship between advertising expenditures X and sales volume Y. So it's pretty significant relationships. Now when you run a computer printout, if we print this, you're going to see that we have something like this. It will give you the predictor, the constant X, and their standard deviations, which gives you S, this, which is the square root of the sample variance we computed before, and gives us an analysis of variance table. And so that's an explanation of how these were obtained. So instead of going over this, I want to show you how you do that on Minitab. So this is a Minitab here. This is how I entered my data. This is the same data we had in the class notes. So that's my sales, advertisements, 10 values, and this is my sales volume. So first I want to go and compute, let's see which one. I want to do a scatter plot, scatter diagram. So I click on this one here. I want the one with the line fitted. Say OK, and then I want here, I want my Y variable, so that's why I want X here. So I enter X or just click on it there, and you notice what I did here is I entered my data, I put Y here and X, so my data starts down here at 1, and I click OK, and boom, I got this value here. And now I want to show you, that's alright. I want to show you how do we do it. You should just go to regression now and click on regression, and I want my Y here. So you enter your Y here, you enter your predictor X here, and you just simply click OK, and look at that output you got. So it tells you what the regression equation is, it tells you what the coefficients were, so that's beta 0 the hat, that's beta 1 hat, so that's your slope, and that's your y-intercept, and these are the standard errors of these, the p-values. So the small p-values indicate these are significant values, and then you have the analysis of variance, which we had before, and the important one here is the p-value, which indicates that we have a good linear model. And that's it. Thank you.